Okay, so hi everyone, I'm Marina Masson. I'm a third year PhD student working in Grenoble, and I will talk to you about how we search for Orphan GRB Afterglows in Rubin LSST data with the alert broker Fink. And Susanna greatly explained how they could be relevant for multi-messenger analysis. So now you probably know what a GRB is, but I will remind you a little bit anyway. GRBs originate from core collapse supernovae or neutron star mergers, and during these really powerful events, they produce a relativistic jet that will produce then the prompt emission. This prompt emission appears as short and highly energetic gamma ray flashes. And then this relativistic jet will collide with the ambient medium surrounding the progenitor, and it will produce this afterglow, so the long-lasting and fading emission that follows the prompt emission. The afterglow can be seen in multiple wavelengths from X-ray to radio, and can be seen at much larger angle than the prompt emission. So if you're off-axis, technically you could see only the afterglow without seeing the prompt emission. And that's what we call an orphan afterglow. And as Susanna said, they can be very long, which is a great opportunity to gather more data about them. But for now, they are hard to find faint and slow transients. So far, there are just a few candidates that were mainly detected in ZTF data. So we expect this to change. We expect to have much more orphan afterglow detection with the Vera-C Rubin Observatory. So this observatory will perform the 10 years LSST legacy survey of space and time. And one of the main goal is to explore the transient optical sky. And we are very excited for the first data, hopefully at the end of the year. For now, ZTF is the best tool to try to detect these orphan afterglows. Because it has like a very large field of view and a really nice cadence of tonight. But it has a nicely limiting magnitude of 20.5, and sometimes it can be not sufficient to observe these orphan afterglows. Unfortunately, the LSST will have a will see the sky in much more depth, with a nightly limiting magnitude of 24.5. And it will also use much more filters, 6 filters in total. So at the end, with all these characteristics, we could expect to have 10 times more data than for ZTF. And of course, this work is part of the Dark Energy Science collaboration. To process these huge amounts of data, we are using alert broker. So how that works? The LSST will use difference image analysis, which means that for each picture of the sky, it will subtract a template. And if in the subtraction of these images, there is a detection that is higher than a specific threshold, the telescope will send an alert. This alert will be sent to all the alert brokers that will receive the LSST data. There are 7 of them, but I'm working just on Fink. So these alert brokers are basically software that will process the data from a telescope and try to identify the data. How that works? So the survey here, LSST will send about 10 millions of alerts per night to the alert brokers, and these alert brokers, through filters that are developed by the community, will try to identify the alerts. And here in this work, I present you how we are trying to develop and implement a filter to identify these orphan gamma burst afterglows. Why would I want to do that? So of course we could gather more information on the GRB physics, about the progenitors, the rates of GRBs, etc. But what's interesting here is because we could perform multi-messenger analysis with gravitational waves, and to try to get an independent estimate of the Hubble constant H0, as it has been done with the 170817. You have here the latest measurement, and in blue you have like the estimate of H naught for binary black holes, and also with the contribution of the electromagnetic counterpart of 170817. And you can see that we still need more statistics, so more events of this kind to get a real constraint on the Hubble constant. Okay, so how do we identify Orphan afterglow? With a Rubin LSST, we will only have the light curves to try to identify the events. And for an Orphan afterglow, the light curve could literally look like this. So you have a fast rise and a much slower decay. And so you can see that they can be very long, as Susanna said. They can be sometimes, they can last for several months, even years sometimes. To compute the light curve, we use the very famous forward shock model and electron synchrotron model, which has been implemented in Afterglow. So that's what we use to compute the light curve. And in this model, there are several parameters that will impact the shape of the light curve, energy, medium density, redshift, observer angle, etc. But also the structure of the jet. So Clément will talk about this tomorrow, I think. But it means that we have a jet with an energetic core and less energetic wings. As you can see, these parameters can impact greatly the shape of the light curve. For example, the jet structure here, the energy, the observer angle, etc. So we need to know what kind of realistic light curve we could get to identify them. So we need to have some parameters distribution. The problem is that we don't have any distribution for these parameters because we detected just a few orphan candidates. So I need to simulate this parameters distribution. So to do that, I use detection of GRBs, of prompt emission, and I will create a population of orphan gamma bursts from this catalog of prompt emission. Here I focus only on short GRBs because they are traditionally associated with neutron star mergers. And the catalog for short GRBs is the SwiftBat catalog SBAT4 that contains a selected sample of short GRBs that were observed by Swift up to 2013. And they were detected because they were selected because their peak flux was higher than this value. And it allowed to create a complete sample of short GRBs. I won't go into much detail on how I create this orphan population, but the general idea is to generate a random configuration of the parameters that I talked to you about before, to compute the gamma flux that would be theoretically received by Swift, and to select the one that have a peak flux higher than this selection criteria. And so at the end, I will have a SBAT4-like GRB population. You have here the example for the energy. So in light blue is the random distribution that I generated at first, and here in darker blue is the energy for all the GRB that respected the criteria that were selected as SBAT4-like SBAT4-like GRBs. So thanks to that, I can create from that I can create an orphan population of a population of orphan afterglows. So I won't go into much detail, but here basically are the distribution that are for this population. And from that, with all this configuration of parameters, I can simulate their light curve and also simulate their observation thanks to a realization of the scheduler simulation for the 10 years of LSST. So if I give a random GRB to this scheduler, I can get an observation of an orphan afterglow. And I just want to point out that, for example, here the peak magnitude for this GRB is 21.5, which means that it couldn't have been observed by ZTF. So we have a great improvement with LSST. And out of all the GRB, the population that I simulated before, only 4% of them have at least 1 point in their light curve. Now we follow a very standard procedure. We characterize the light curves with some straightforward features, the duration between the first detection and the peak, some rates in different parts of the light curve to characterize how it rises and how it decays, and also the colors, because we expect to see red events. So it could be, it is a great feature to take into account. Now we want to have, to make the characterization more stronger. So we decided to fit the light curves. And to do that, we rescale all the data to the R band. So we rely on the fact that for synchrotron emission, the flux is scaled as like this. And here the beta value, so the spectral index can take two values, can take several values between these two values here. And we don't know the one that we should use. So the idea is to take several values for this spectral index and to keep the one that minimizes the distance between all the points. And here you have an example. So we have the light curve that I showed you before. And after rescaling all the points, you have just all the points on the R band as they would have been detected on the R band. It allows us to fit the light curve more effectively, more efficiently, thanks to an empirical function. And at the end, we have all these features that allowed us to characterize these orphan light curves. So we have to distinguish all these orphan for all the other alerts that are the background. And this background, I use Elastic, which is a data set that contains synthetic light curves for basically all the other alerts that we could expect to see with LSST, so supernova, AGN, kilonovae, etc. But the point is that there are no orphans. So for all the alerts contained in these data sets, I computed the same features than for all the orphan afterglows. So at the end, I can create a machine learning algorithm that take these features and is trained to recognize which one are the orphans and which one are other alerts. For now, it works pretty well because it recognized almost like 84% of the orphans and reject almost all the background, which is what we need because we will get, as I said, about 10 millions of alerts per night, which is huge. So we need to have a filter that reject a lot of background because at the end we want to have the light curve that we could observe by eye. So for now it works pretty well. Here are examples of light curve that pass this filter. So here a very nice orphan afterglow simulation, and here this supernova that has not so much points but still pass the filter. But as it doesn't have many points, maybe I would not consider it as a good candidate anyway. So in conclusion, we try to implement a filter in Fink to identify these orphans. There are still some work to do to test this filter, of course, because for now we just tested on simulation. So we plan to adapt this filter and test it on ZTF data. And also there are some discussion to try to see if we detect an orphan candidate, a good one, how we could try to see if there is a joint gravitational wave detection. If we could see if we could estimate the T0 of the orphan. And that's all. Thank you for your attention.
Good. Other questions?
Thank you very much. I just want to check there's something I didn't quite follow. So you took the SBAT sample and you used essentially the parameters you could derive from that as representative of the true distribution to go into your simulations. Is that right? So you simulated events based on the distribution. So how did you get the jet opening angle from that? Because that's something that's notoriously sort of unconstrained from generally
So
data.
for the SBAT4, I consider on axis, and then the observing angle is just randomly distributed. Like I generated randomly.
No, but, sorry, when you had a distribution of theta c though, like the core opening angle, like on is what I mean. So that the top right one there, yeah. How did you get that?
So at first I generated in a uniform distribution, and after applying all the criteria to get this orphan distribution, this is what I get, basically. I don't really understand why it gives me such a weird distribution, and this is something I have to look at. But for now, this is what I use.
Okay.
But at first, it was completely uniform. It gave me that after.
Okay. Yeah. Okay. Thank you.
There's a question on Zoom. Just go ahead. We should be able to hear you, right?
Can you hear me?
Yes.
Hi, Erin. Marina. Nice talk. I was wondering, do we expect often afterglow only from short GRBs? Why did you only use a short GRB sample for the simulation?
Yes. So you see here I use only short GRBs because we were talking about multi-messenger analysis, but we expect also to have orphan afterglows from long GRBs, and they could be very interesting to look at because long GRBs are expected to be more energetic. So of course, this is something that I studied, but just for this presentation, I just focus on short GRBs.
Thanks.
Maybe I can ask a quick question. So did you check how fast you can find your afterglow? I mean, how many points do we actually need, and how much data? Of course, with more data, you get more and more confident. But how fast can you be in the most optimistic case?
So in the most optimistic case, I can expect to have like 5 points, and this is the limit that I put to compute all the features. And in some cases, I can have just 5 points, and it gives me an orphan afterglow.
So, but 5 points based in time with a cadence of 3 days is 2 weeks. Is that the right interpretation, or can you have 5 points but at the same night with different filters?
Not on the same night. I think it's not enough. But in several days, yes.
Thanks.
Also, I have a quick question. I may have missed this at the beginning of your talk. So how many events, how many of these orphan afterglow events do we expect with like 10 years of LSST? I think you said tens or something. Did I hear that right?
No, I didn't.
Okay.
I didn't say. So I don't know. So there were some estimation, but they are quite old. I think they're like from 10 years ago, where we could expect at least 50 orphan per year with LSST. But maybe the number are not really.
There's a lot of error.
Yeah, maybe they changed. So actually, I don't know. This is something that I would like to check actually.
Okay, because that's very relevant in terms of like constraining the Hubble constant that you mentioned, right? So if we don't know the with the distance inclination degeneracy, if we don't know. If we just look at orphan afterglows, right? So then we probably need maybe hundreds of events to actually really constrain the Hubble constant further and to break the tension. Anyways, that was just the background.
Yeah,
Thank you.
You're right.
Thanks a lot. And thanks all the speakers of this